This is Chapter 9, QoS Concepts, where QoS stands for Quality of Service. There are 5 sessions in this chapter. 9.0 Introduction, 9.1 the Network Transmission Quality, 9.2 Traffic Characteristics, 9.3 Queuing Algorithms, 9.4 QoS Models, and 9.5 the QoS Implementation Techniques. Let's begin with 9.1 the Network Transmission Quality. As modern networks continue to carry more types of traffic, simply forwarding packets on a first-come, first-served basis is no longer sufficient. Today's network carry email, web browsing, file transfers, voice over IP, the VoIP, video conferencing, streaming media, cloud applications. Each type of traffic has different performance requirements. This is where quality of service, or QoS, become very important. Why is QoS needed? Not all network applications have the same requirements. For example, email can tolerate delays of several seconds. File downloads can slow down without causing major problems. Voice calls require very low delay. Video conferencing requires low delay and low packet loss. If voice and video packets are delayed too long, user may experience choppy audio, frozen video, poor call quality. So QoS helps prevent these problems by giving higher priority to delay-sensitive traffic. In the previous lesson, we learned the quality of service helps prioritize important network traffic. But when is QoS actually needed? The answer is during network congestion. What is network congestion? Congestion occurs when more traffic arrives than the network can transmit. This commonly happens when multiple incoming links send traffic to one router. Many packets must live through a single outbound interface. A fast interface sends traffic to a slower interface. Think of it like a highway. Several highways may merge into a single lane. When too many cars arrive at once, traffic slows and a traffic jam forms. The same thing happens with network packets. This figure illustrates one of the most important concepts in QoS, that's the priority queuing. When a router experiences congestion, it does not have to treat every packet the same. Instead, QoS can classify packets into different priority queues. Let's talk about different types of traffic. Notice that 3 different types of traffic are entering to the router. They are the voice over IP traffic, financial transaction traffic, also the web page traffic. Although all 3 are important, they do not have the same network requirements. High priority queue. The voice traffic is placed in the high priority queue. Why? Because voice communication is very sensitive to delay and jitter. If voice packets arrive late, users experience choppy audio, delays, broken conversations. For this reason, voice traffic is usually given the highest priority. We also have the medium priority queue. Financial transactions are placed in the medium priority queue. These packets must arrive accurately and reliably, but they can tolerate slightly more delay than voice traffic. Examples include credit card transactions, online banking, business applications. And then we have the low priority queue. Web traffic is placed in a low priority queue. For example, browsing websites, downloading files, software updates. A slight delay in loading a web page is usually acceptable, so this traffic can wait longer during congestion. Now let's talk about scheduling the queue. After packets are classified into queues, the router schedules them for transmission. Notice the packet leaving the router. The router sends more packets from the high priority queue, then the packets from the medium priority queue, then packets from the low priority queues. This ensures that delay-sensitive applications receive better service. Bandwidth is the maximum amount of data that can be transmitted over a network in 1 second. It is measured in bits per second, or BPS. Common bandwidth units include kilobps, that's the kilobits per second, and we have the Mbps, which is the maximum bits per second, Gbps, that's the gigabits per second. For example, a network interface rated at 10 Gbps that can transmit up to 10 billion bits every second under ideal conditions. Keep in mind that bandwidth is the capability of the link. That's not the actual amount of traffic currently being transmitted. This figure shows 3 common locations where network congestion occurs. These are also the best places to implement quality of service. Let's look at each example. The first example is aggregation. Notice that multiple network links are sending traffic into a single switch or router. When traffic from many users is combined onto one outgoing interface, the total traffic may exceed the available bandwidth. As a result, packets begin to queue. Delay increases, packets may eventually be dropped. This aggregation point becomes a natural location for QoS to prioritize important traffic. The second example shows a speed mismatch. Notice the two interface speeds, 1000 megabits per second, also the 100 megabits per second. Traffic is moving from the faster link to a slower link. The 1000 megabits per second interface can send data much faster than the 1 megabits per second interface can forward it to. Because of this mismatch, packets arrive faster than they can leave. The output queue grows, congestion occurs. So QoS helps determine which packet should be transmitted first while others wait. The third example shows a LAN to WAN connection. Inside the organization, the LAN operates at 1000 megabits per second. However, the WAN connection to the internet is only 100 megabits per second. Many users share this single WAN connection. During busy periods, the WAN interface becomes the bottleneck because it has much less bandwidth than the internal LAN. This is one of the most common places to implement QoS. For example, voice traffic receives high priority. Business applications receive medium priority. File downloads and web browsing receive low priority. We have already know that different types of delay occurs as a packet travels across the network. Let's look at each one. The first type is the codec delay. A codec compresses voice and video data before it's transmitted. This compression takes a small, fixed amount of time. For example, during a voice over IP call, your IP phone must first convert your voice into digital data before sending it across the network. This processing time is called the codec delay. Next is the packetization delay. After the data is compressed, it must be placed into the packets. The device adds the necessary protocol headers such as the IP header, UDP header, RTP header. The time required to create a packet is called a packetization delay. Like codec delay, this is generally a fixed delay. The third type is queuing delay. This occurs when packets must wait in a queue before they can be transmitted. Queuing delay depends on network congestion. If the network is busy, packets wait longer. Delay increases. If the network is not congested, packets are transmitted immediately. Queuing delay is very small. This is only delay that QoS can significantly reduce by prioritizing important traffic. Next is the serialization delay. Serialization is the process of placing the bits of a frame onto the physical link. The time required depends on the size of the frame, the speed of the link. For example, a 100 megabits per second interface takes longer to transmit a frame than a 1 gigabits per second interface. Serialization delay is usually fixed for a given frame size and the link speed. After the bits are on the wire, they must travel to the destination. This travel time is called a propagation delay. Propagation delay depends on the physical distance, the transmission medium, such as fiber or copper. For example, a packet traveling across the country experiences more propagation delay than one traveling across a local network. QoS cannot reduce propagation delay because it's limited by the law of physics. In addition to delay, another important factor affecting the network performance is the jitter. Jitter is the variation in the arrival time of packets. In other words, packets do not arrive at constant intervals. This is especially important for real-time applications such as voice over IP, video conferencing, live video streaming. By default, routers and switches process packets on a first-come, first-served basis. This means packets are forwarded in the same order they arrive, without considering the type of traffic. If the network is not congested, this approach works well. However, problems occur when congestion develops. Packet loss without QoS. When congestion occurs, packets begin to fill the router's output queue. If the queue becomes full, the router must drop packets. Without QoS, all packets are treated equally. This means a voice packet has the same chance of being dropped as an email packet or a web browsing packet. For delay-sensitive applications, such as voice and video, packet loss can seriously reduce quality. This figure illustrates how a playout delay buffer, also called a jitter buffer, helps improve the quality of voice over IP calls. Notice the packet at the top of the figure. They are labeled audio stream of packets received with jitters. The packets do not arrive at evenly spaced intervals. Some packets arrive early while others arrive late. This variation in arrival time is called a jitter. This figure shows what happens when jitter becomes too large for the playout delay buffer to handle. In the previous example, the playout delay buffer successfully smooths out the smooth variation in packet arrive times. However, there's a limit to what the buffer can compensate for. Notice the packet at the top of the figure. The packets arrive with very uneven spacing. Some packets are delayed much longer than others. This condition is called excessive jitter. The playout delay buffer temporarily stores incoming packets and waits for them to arrive. Its goal is to play the audio at regular intervals. However, the buffer cannot wait forever. If a packet arrives too late, the audio must continue playing. Otherwise, the entire conversation would pause while waiting for one delayed packet. In this example, one packet arrived after the playout deadline. Because the receiver has already continued playing the audio, the late packet is discarded. Notice the missing packet is in the output stream. The figure states packet is dropped due to excessive jitter. Even though the packet eventually arrived, it is too late to be useful.